tolerate this echo for the time being. So Masaki did his PhD in physics from University of Tokyo from the Kohomoto group. And then in the same university, he worked as a JSPS research fellow. And then he moved to Department of Applied Physics in the University of Tokyo in the group of Nagaosa. Then he was a Killam postdoctoral fellow in the AFLEC group. So in February 1998, he became an associate professor, Department of Physics, Tokyo Institute of Technology, professor, Institute of Solid-State Physics, where is he right now? University of Tokyo, and he's also senior scientist in Kavli Institute for the Physics and Mathematics of the Universe. He has got numerous awards, and to mention some of the few, his Ryugo Kubo Memorial Award in 2003, CEST Award for Young Scientists in 2005, JSPS Prize in 2008, and recently he got the award for Science and Technology Research category in the year 2022 from the Minister of Education, Culture, Sports, and Technology, Japan. Well, Masaki is going to tell us about quantum criticality when the system is conducting, or protecting quantum criticality when the system is conducting or insulating. Please.
Okay. Yeah, thanks very much. So first of all, I'd like to thank all the organizers. Yeah, actually, I'm supposed to be organizer, but I have done very little, almost nothing to organize this because yeah, we got the idea of this workshop when I met Indra in APCTP meeting some years ago. So we initially planned this in 2020, but of course it's cancelled, postponed by the pandemic. So actually, my organizer job was taken over by Kosho Kakura, who is sitting there. So he did the most of the work from Japan side. So I should thank him and apologize. And yeah, but finally this meeting materialized. So I'm very happy about this. And also, this is my first visit to Kolkata, which I'm enjoying very much. And also, I cycled to various places, including this Salt Lake, just southeast of the both institutes, maybe 5-10 kilometers from the institute. Yeah, you can have a nice sight. Okay, so today I'd like to talk about protecting quantum criticality. But actually, a few days ago, we had a nice talk by D.D. Sarma. So I tried to make this as a kind of sequel to his talk in some sense. But I'm afraid that some of you are very familiar with what I'm going to talk about. For those of you, I apologize, but I saw that there are people from very different backgrounds. So I thought maybe talking about very fundamentals would be helpful. But in the latter half, or maybe latter quarter of my talk, I will try to sketch some of the very recent developments, which might be also interesting for experts. Okay, so why? No, it's not exposing. Okay. Yeah, so I like to discuss the very fundamental classification of materials. So yeah, in elementary school, yeah, actually, I took this from a video for elementary school kids for grade 3. So we have battery and light bulb, and connect this through the metallic part of the scissor. Then this light illuminates, although, sorry, it's not very clear on the picture. But if you use the handle part of the scissor instead, then the light bulb does not illuminate. So this is because metals are conductors and the plastics are insulators. So everybody knows about this. But if your kids, son or daughter or your brother ask you why this is so different, then actually answering to this question is rather, difficult. But we have some idea, and it's still frozen. What's going on? Yeah, maybe we disconnect. Yes. I can just use people. Yeah. So let's see. Okay. So yeah, if we just consider system of free electrons, we understand pretty well how the conductors are different from insulators. That is, so in free electron systems, we can understand the system in terms of band theory or single electron energy levels. So let's say this box shows a band. That is, there is a continuum of single electron energy levels within this box. And at zero temperature, because electrons are fermions, you fill these lower energy states by electrons. And upper end of this filled levels is the Fermi level. And if the Fermi level lies within the band, then if you apply the electric field, you can easily excite those electrons to these empty energy levels. Then the current flows. So this is the typical situation for metals, which are conducting, electrically conducting. But if there's a band gap, that is, there are single electron energy levels within this box and this box, but if there is no single electron energy levels in this region, it's called band gap. And if the electron just fill this lower band, then you need extra energy to create any excitation. So in this case, if you apply weak electric field, then nothing happens. So this is an insulator. So, okay, so this is very well understood. And probably you run this in undergraduate solid state physics or something like that. But what is important is that this diagram, band structure just shows you the single electron energy level. So this is only valid, at least strictly speaking, when electrons are not interacting. So, but in real world, of course, electrons are interacting, but somehow in some materials, you can basically ignore the interaction and understand the properties of material in terms of almost free electron theory. But in general, electrons are interacting. Then we can no longer, at least generally speaking, describe the physics in terms of single electron, because single electrons scatter with each other, and the state becomes pretty complicated. So at least in general, we cannot apply the band picture. But still, we want to distinguish conductor from insulator. And indeed, the real material can be either conductor or insulator. And in this case, we should use the many body energy, that is the total energy of the system, instead of the single, the energy of single electron. And typically, okay, so any system has a ground state, which is the lowest energy eigenstate. But there are, roughly speaking, two types of the system. One of which is the gapless system, which means that there is a continuum of excited states just above the ground state. So in this case, you can create excitation by infinitesimally small energy. So basically, this corresponds to conductor, although, okay, so this is not completely equivalent, as we will see, but very roughly speaking, this corresponds to conductor because even if you apply very weak electric field, you can create excitations and accelerate electrons. But in some systems, there's an energy gap above the ground state, which means that you need to give at least this amount of energy to create any kind of excited state. And I stress that this is the energy gap of many body energy, not just a single electron energy, but of course they are related. So in this case, the small perturbation does not change the ground state, and very roughly speaking, this corresponds to insulator. So in order to distinguish conductor from insulator, first, it is important to distinguish two cases, that is, whether there is a many body gap above the ground state or the system is gapless. So we want to distinguish these kind of situations. Okay, so this is one of the basic questions in condensed matter physics or quantum many body problem. And actually, many people are interested in this kind of questions, but somehow I realize that people have different attitudes towards this question depending on your background. Yeah, in fact, yeah, different communities speak different language. So this is, I suppose, Bengali, but I have no idea what this guy is talking. And this is Japanese, and you have no idea probably what they are speaking, although I can easily read. But these days, there's a Google Translate or whatever, and you can just scan by a smartphone, and it can show you translation. And that's very useful, but it's not always sufficient, because even if you translate, if you have a good dictionary and translate each word, each sentence, then still sometimes you don't know what they are talking about, because different communities have different background and different point of view, and that also happens in physics, as you probably experience. So what I found from talking to solid state physics is that solid state physics somehow the natural way of thinking is that electrons form metals by default. If you do nothing, then you have just a Fermi gas or Fermi liquid, and the system just conducts electric current. But some materials are insulator, of course. But in solid state physics viewpoint, I think you need something to make the system into insulator, like a charge density wave, instability, and so on, so on. You need something. I think this is maybe traditional solid state physics point of view. But if you come from StatMech, then yeah, you can have a different idea. Because if you have a many body gap, delta, that is separation between the ground state and the continuum of the excited state, then you can derive this equation rather easily. That is, this is a correlation function in time direction, or more precisely imaginary time direction. So you analytically continue real time to imaginary time by replacing t by I tau something. Then you can at least theoretically consider correlation function of some operator to imaginary time direction. Then if there is a many body gap, which is non-zero, then this imaginary time correlation function generally decays according to this exponential law. And this delta determines how fast this correlation function decays in imaginary time direction. That is, delta is inverse of correlation time. So after imaginary time, 1 over delta, the the correlation decays. Oh, okay. So there are some questions. Maybe I should. What do you mean by many body gap? Generally, when we differentiate between insulator and metals. Okay, so well, so that's also different. So many body gap is really the separation between the total ground state energy versus lowest of the excited state. That's a difference in total energy. But for example, if you have a band insulator, then many body gap is basically equal or maybe twice of the band gap. They are related. But if you have strong interaction, then generally speaking, you can no longer talk about single particle density of state and so on. So I want to discuss more general interacting systems, and many body gap is always very defined. So yeah. So this is imaginary time correlation function, and it decays after correlation time 1 over delta. So yeah, many body gap gives the inverse correlation time. And the correlation length is a similar concept in spatial direction. In very general sense, this correlation length and correlation time are different, but in many cases, they are open proportional. Okay, I'm not going to discuss when they are proportional and when they are not, but in many cases, correlation length is also proportional to correlation time, which means that the correlation length is proportional to 1 over the many body gap. So that means that if you have an insulator, which implies the system has a gap, then correlation length is finite. These are characteristics of off-critical system, non-critical system. And if you have a gapless system, then it implies that the correlation length is 1 over 0, which means that the correlation length diverges, infinite correlation length. So this is a signature of the critical system. So in fact, this is not just an analogy, but in many cases, you can make this correspondence precise. For example, this is a quantum transverse field Ising model, the most prototypical model, spin model for quantum critical phenomena. So the first term is minus sigma z. So this is exactly like a classical Ising model. But the second term, g times sigma x, is so-called a transverse field term because x is orthogonal to z. Then this transverse field term flips sigma z because sigma x, if you apply sigma x to upspin, it becomes downspin, and if you apply sigma x to downspin, it becomes upspin. So this second term introduces quantum fluctuation. So by changing this value of g, you can drive the strength of the quantum fluctuation. So if g is small, then the ground state is basically the ground state of the classical Ising model. So all spins up or all spin down. So it's an ordered state. But if g is sufficiently strong, okay, so if g is infinity, then the spins are completely disordered in SZ basis. So at some finite value of g, there is a critical point. So you can separate ordered phase from disordered phase, and there is a critical point. And this critical point exactly corresponds to the standard Ising transition in classical stat-mech in one higher dimension. That is, if you consider d-dimensional system for this, then ground state quantum phase transition corresponds to classical Ising transition in d+1 dimension. That this correspondence can be made more mathematically. Okay, so to recap, in Ising model, the critical point is just a single point. So in classical stat-mech context, the horizontal axis corresponds to temperature. So if you go to very high temperature, the system is disordered. And at low temperature, spins are ordered, and there is a critical temperature. And only at the critical temperature, the correlation function, correlation lengths diverge. And at all other temperatures, except for this critical point, the correlation length is finite, which corresponds to this gap spectrum for this quantum model. So in fact, this, if you study many-body quantum gap, many-body gap for this transverse field Ising model, you find a finite gap for all the values of G except for this critical point. And only at this critical point, you have this gapless or critical spectrum. So from StatMech point of view, so the gapless or critical systems, which roughly corresponds to conductors, are rather special because you have to tune this parameter like G or something to the critical point. Then only at the critical point, you have a gapless spectrum. Okay, so this is a StatMech point of view. But from this viewpoint, it's kind of mystery that there are so many critical systems or so many conductors without introducing any fine tuning. You pick up some piece of metal, it's already conducting. So you don't have to apply pressure and tune the pressure to the critical point in order to make this piece of metal conductor. You just pick up metal and it's already conducting. So apparently there are many gapless or critical systems in condensed matter physics, which do not require any fine tuning of parameters, especially metals. So this may be, maybe so natural for solid state physicists, but from StatMech point of view, this is kind of mystery. So there must be some reason or mechanism that protects the gaplessness or quantum criticality in many condensed matter physics systems. And what I want to discuss is to answer at least partially to this question. Of course, I cannot answer about every metallic system, but at least I'm going to present one of the mechanisms which can protect this gapless nature or quantum criticality in some sense. So yeah, and although the title of this workshop is about computation method, but I'm not expert on computation method, so I'm not going to give you any concrete algorithm to compute anything, but rather give you some general principle or general constraint depending only on the symmetries of the system. And of course, real materials are much more complicated, but here I want to discuss just a very simplified model, lattice model, like this Hubbard type model. So this is a spinless Hubbard model, I would say. So electron hopping and interaction between nearest neighbor or something like that. Then this kind of system generally has U1 symmetry because you can attach this extra phase E to I theta for the annihilation operator Cj. Then creation operator receives opposite phase. But then if you do this global transformation, then this Hamiltonian is unchanged because extra phase picked up by Cj is cancelled by extra phase picked up by C dagger here. So the Hamiltonian has this U1 symmetry because theta can be any real number, continuous symmetry. And as it is generally the case, thanks to the Navier theorem, if there is a symmetry, then there is a corresponding conserved number. And in this case, this Hamiltonian conserves the particle number. The total number of particles is conserved. Then, of course, this is basics of any solid state or condensed matter physics, but can we say something about the energy spectrum, whether the many body gap is zero or non-zero from this symmetry of the system? And the answer is yes. And actually, maybe first known example, known mechanism which protects the gapless nature of the quantum many-body system is actually Nambu-Goldstone theorem. That is, if you have continuous symmetry in the Hamiltonian, like a U1 symmetry, and if this continuous symmetry is spontaneously broken, like in anti-ferromagnet, ferromagnet, then the Nambu-Goldstone theorem states that there must be gapless excitation. So under these general assumptions, then the spectrum must be always gapless. So this is, of course, very important theorem with many, many applications in condensed matter physics. For example, if you have anti-ferromagnet, ferromagnet, then there are spin wave excitations which are gapless. And intuitive understanding, and also you can make this intuitive understanding into rigorous mathematical proof, is that if you have spontaneous breaking of continuous symmetry, you have ordering of, let's say, spin or order parameter, and because the symmetry is continuous, this order parameter can rotate continuously, but in the ground state, the system picks up one particular direction. Then once the system chooses one particular direction, that is nothing but spontaneous symmetry breaking, you can try to twist this order parameter very slowly. And so in the ground state, let's say all the spins are pointing up, but then you try to twist these spins very, very slowly. Then you can create a low energy excitation. And this is nothing but Nambu-Goldstone. And this can explain many gapless systems, like phonons in acoustic phonons in solids, gapless, and you can say that this is because of Nambu-Goldstone theorem, because crystal breaks spatial translation symmetry spontaneously, and so on and so on. But this is, of course, not the complete answer, because, for example, if you consider metallic system, then metals do not break any continuous symmetry. So we need more other mechanisms which can protect or guarantee the gapless critical nature of the system. And the question is, are there other mechanisms other than Nambu-Goldstone theorem? And the answer is yes, at least when there is also a lattice transition symmetry. Okay, and so that mechanism is what is called Lipschutz-Matisse theorem, and its various generalizations. And the history of this theorem is very long. The first paper was by Lipschutz-Matisse in 1961, that's more than 50 years ago. But at that time, the theorem was not really appreciated because it was only discussed for very limited cases. But now we appreciate that this old theorem is very useful. And in particular, this is one of the very general mechanism which can protect the gapless nature of the system. Okay, so this part I basically follow the original argument by Lipschutz-Matisse, and what I'm going to tell you what this theorem can tell you about this many particle system. So here I want to discuss one-dimensional system first, because the original argument was basically for 1D system. So for example, we can consider 1D spinless Hubbard model like this. So you have a system, one-dimensional chain, and I impose a periodic boundary condition, and these red dots represent each site. Then electron spinless electron can hop to neighboring site to the right or left with this parameter minus t. And there's a nearest neighbor interaction, density interaction like this. But this particular model actually happens to be exactly solvable by Bethe and that. So we know the answer, but the powerfulness of this theorem is that actually you can generalize to more complicated models. Like you can introduce nearest neighbor hopping or nearest neighbor interaction and so on and so on. But as long as you keep the symmetry, then you can apply this theorem. But for illustration, you can just imagine this simplest model. Then this model has U1 symmetry, as usual. The particle number is conserved. But then this model is also translation invariant. That is, you can shift each side to the right, then yeah, Cj becomes Cj plus 1. But still, this model is invariant, at least under the periodic boundary equation. So this is a translation invariant system. Then ingenious argument by Lipschutz-Matisse was to create some variational state. So we start from the ground state. So this is a Hamiltonian and the ground state and the ground state energy E0. But of course, for very complicated models, we don't know exactly what is the ground state energy or what exactly is the ground state wave function. But for this argument, you don't have to know exactly what are the ground state or ground state energy, but you just need to assume that the existence of ground state, and they generally do exist. And then the idea is a bit similar to Nam-Goldstone theorem, although different, because now I want to twist the system very slowly. And twisting means that you want to add extra phase to this creation annihilation operator. That's like a rotating spins. And in order to then now, so if this theta angular parameter is uniform throughout the system, then this is just like global symmetry transformation, U1 transformation. But in order to create excited state, you want to twist the system, which means that you want to change this phase factor theta depending on the location of spin. And that can be done using this so-called twist operator U that is exponential of 2 pi I times J. J is the site index, location of spin, over system size L times the number operators Nj. So if you just use a constant theta here, which is independent of J, you can generate global U1 transformation. But now this phase factor depends on the site index J. So if you do this twist, then Cj is transformed to Cj times this phase factor. And the phase factor is proportional to this site index. So this twists the spin gradually. So first you don't twist, and the next spin, next wave function, you twist a little bit, and you increase the twist angle twice, 3 times, 4 times, and so on. So on. But so if you change the twist angle, then usually you will have a problem with the periodic boundary condition. But for this twist, this is consistent with periodic boundary condition, because if you go to J equals L, then twist angle becomes 2 pi times L over L, which is 2 pi. But twisting by angle 2 pi is equivalent to twisting with angle 0. So this is completely consistent with periodic boundary condition. Okay, so now I want to, or actually Lipschutz-Matisse basically showed that the variational states, the created in that way by twisting the ground state wave function has very low energy, at least for 1D system. And that can be proven in one page like this. So I want to evaluate expectation value of Hamiltonian by U psi 0, the twisted state, minus ground state energy. That is nothing but expectation value of Hamiltonian by original ground state psi 0. So I want to evaluate this one. But this expectation value can be computed by evaluating this U daga Hamiltonian U, this twist of Hamiltonian. And if you twist Hamiltonian, then Hamiltonian consisted of this C daga C hopping term. And for uniform twist, uniform transformation, the phase factor cancels with each other. So Hamiltonian was invariant. But with this twist operator, the twist angle depends on each side, which means that the phase factor coming from C daga at J plus 1 and the phase factor from Cj do not completely cancel. So you have an extra phase remaining here, e2 minus 2 pi I over L. But here you only pick up the difference between phase factor from neighboring side. So this mismatch is only of order of 1 over L, 2 pi I over L. That is the key point. And this density-density interaction is invariant because this twist does not change the density or number operator. So now I want to evaluate the difference between this twisted Hamiltonian and the original Hamiltonian for very large system type, because we are interested in thermodynamic very large system. So now you can expand this exponential by 1 over L. Then zeroth order term completely cancel between these two, of course. But then you pick up the first order in 1 over L, which looks like this, something times C daga C minus C daga C. But this is like a current operator. So if you take ground state expectation value, then this term vanishes. Then the next contribution is second order in 1 over L. So if you expand, you will pick up T times 2 pi over L squared and the summation over C daga C plus C daga C. So this is like a kinetic energy term. So if you take expectation value, then you have non-zero expectation value from this. And also you need to sum over all sides, which means that you will correct something, some constant times system size L. But here you already have 1 over L squared because you expanded this exponential to second order. So you have 1 over L squared in the front, and you pick up something times order L. So if you multiply, entire expectation value is still order 1 over L, and you have higher order correction. So that means that the expectation value of energy in the new variational state, U psi 0, may be higher than the ground state energy, but only by order of 1 over L, which means that if you study larger and larger system, the energy difference gets smaller and smaller, which means that this twisted state, U psi 0, must be very low energy state. Maybe just above the ground state, but only slightly. But this is still not enough to say anything, because I haven't assumed any spontaneous symmetry breaking. So if you start from the ground state and twist this ground state by operator U, but this state could be almost identical to the original ground state. If that is the case, this new state having very low energy is kind of trivial. You twist, but you obtain the original state, ground state, then ground state has very low energy. That's trivial. So in order to say something about the energy spectrum, you have to show that this U times psi 0 is different from ground state, or they are also one. If you can show that, then you can say some non-trivial statement about the energy spectrum. And for that, the translation symmetry is very useful. So the Hamiltonian was translation invariant. So the ground state must be eigenstate of translation operator. So this is unitary. So eigenvalue has absolute value 1. So let's say the eigenvalue was e to ip0. P0 is a ground state momentum or something. Then evaluate u daga tu, so twist of this translation operator. Then u daga and u almost cancels. Okay, so if there is a no t, then u daga is of course inverse of u because this is unitary, so they cancel each other. But if you translate, this u is the position dependence twist, and if you translate by one side, you also change the twist angle. So u daga and u do not cancel with each other if you sandwich this translation operator. So the remnant phase factor is given by e to 2 pi I times summation of nj, because from u daga you have minus j plus 1, and from u you have 2 pi ij. So they don't cancel, but you pick up this extra phase factor. But this uncancelled extra phase factor is 2 pi I times summation over this particle number operator divided by system size. But this is nothing but the total number of particles, which is constant. So you can replace this by constant, that is number of particles. So you can write this relation as u daga tu is e to 2 pi nu I times the translation, where nu is the total electron number divided by system size. That is often called filling factor, the particle number per side. So this means that so t and u have non-trivial commutation relation if this filling factor is not integer. If nu is integer, then this becomes trivial. So this exponential becomes 1, so you can forget about this. But if nu is not integer, then t times this variational state, u psi 0, you can exchange order using this commutation relation. Then you get e to ip0 plus 2 pi nu I. So you have extra phase factor here times u psi 0, which means that this twisted state has new eigenvalue, this new eigenvalue for this translation operator, which is different from the original ground state if nu is not integer. So that means that if filling factor is not integer, then this u psi 0 must be different from original ground state, and it has low energy compared to the ground state. So the statement is that if the filling factor is not integer, then for finite size system, there must be low energy states, multiple low energy states, including ground state. So there are two possibilities. One is that the system is gapless. That is always possible. But if you have a gap, then you must have a degenerate ground state below the gap, because we have already produced low energy states which are different from ground state. So this is very simple argument, but already very powerful, because this rules out the simplest possibility that so in general, if you have just a featureless trivial insulator, then the ground state would be unique. But if you have global symmetry, U1 symmetry and translation symmetry, and if filling factor is not integer, then you cannot have a unique ground state below the gap, which means that physically speaking, you cannot have, yes.
This is the integer can be only one. Cannot be 2 or 3, right?
If we consider boson, then yeah. So actually, this argument does not depend on the statistics of the particle. So yeah, for boson case, yeah, and also I will discuss the spinful electron case, in which case you can. Yeah, so for non-integer filling factor, one of these two are possible, but you cannot have just a featureless trivial insulator in something. So that's a statement of the Lipschutz matrix theorem. Yes. Okay, yeah, someone is raising hand. Any question? Speak up.
Can you get the physical value of B for the case of earlier?
Well, this argument is kind of general, so you need to do real calculation to know the critical value. So this theorem is pretty general, so it doesn't care about the value of parameter, but it constrains the possibility.
I'm saying integer is not enough to get.
So even for integer filling, of course, you can have a gapless spectrum, but this theorem allows trivial insulator phase as a possibility. But you need to do real calculation to figure out which is the case. But at least this gives some guidance. Okay, so actually the intuitive picture is quite simple. So basically, in order to open up a gap, then particles must be locked onto the lattice. So it has to have a commensurate filling. So for example, if you have one particle per unit cell, this is already fractional, but you can form CDW, charge density wave state like this. You have a particle here, empty here, particle here, empty. So this is like a CDW state. Then you can open up a gap by having the degenerate ground state. But if you dope the system, as experimental colleagues do, you introduce extra particle here. Then this extra particle, doped particle, has no reason to stay here. It can hop to the next empty site. So it tend to move around. So roughly speaking, a physical way of stating this is that by doping the particle or hole, you introduce mobile carrier, then the system becomes gapless. And that is completely consistent with this Lipschutz matrix theorem, right? Argument. Okay, so maybe I want to comment briefly about Lipschutz matrix for spinful electron. So of course, real electrons have spins. So in condensed matter physics, we often consider a Hubbard model like this. Of course, to represent more realistic material, you may need to introduce other orbitals and so on. But this theorem is very general, so you can also deal with more complicated models. But for illustrative purpose, let's consider this kind of simple model. Then, so now creation annihilation operator or number operator has extra index corresponding to spin up or down electron. But this Hamiltonian conserves number of upspin electrons and the number of downspin electrons, which also means, of course, total electron number is also conserved. And we often discuss a case of so-called half filling, which means that for this model, each site can accommodate 2 electrons, upspin and downspin. But if you give 1 electron per site on average, then total electron filling, that is number of electron per site, is 1/2 of the maximum 2, that is nu is 1, which is integer. So then it seems that the Lipschutz matrix theorem cannot be applied, or even if you apply, you get a trivial result because the nu is integer. But for this case, it's useful to consider filling factor for or number density for upspin electrons and downspin electrons separately. And usually we consider a case both upspin electrons and the downspin electrons are 1/2 per site. So in this case, you can apply twist operator to only upspin electron or downspin electron. Then actually, we can obtain a non-trivial statement from Lipschitz matrix argument. That is a ground state degeneracy. So if the system has a gap, then you must have a ground state degeneracy, or the system can be gapless. But the important point is that so we cannot say from this argument what kind of gapless excitations we have. So in fact, in 1D at least, there's a phenomenon called spin charge separation. So the excitations can be just a genuinely spin excitations without charge degree of freedom, or charge excitations without any spin degree of freedom. So in fact, this model is again exactly solvable by Weissenbruch. So phase diagram is pretty well known. So if you draw phase diagram as a function of this Coulomb dispersion parameter U, then for positive U, you have so-called Mott insulator. So this is insulating actually. That means that you have excitation gap for charge excitation. But still, Lipschitz matrix theorem tells you that you must have a ground state degeneracy or gapless excitations. In fact, there are gapless spin excitations for positive U, because effective model is spin 1/2 Heisenberg anti-ferromagnetic chain. But if you go to negative U, then spin gap opens up, which is called Lusa-Emery limit, which you discussed. In this Lusa-Emery limit, spin gap opens up, but there are gapless charge excitations. So in negative U regime, actually the system is conducting electricity. So the system can be charge insulator and spin conductor, or spin insulator and charge insulator and spin conductor. But you cannot open all the excitation gap at the same time without having the ground state degeneracy. That's a constraint from the Lipschitz matrix. Okay. Skip this. Okay, so those are well-known things. Maybe I should quickly go mention this. Okay, so this Lipschitz matrix argument actually was first developed for spin chains, not for Hubbard model or something. But actually, spin chains and Hubbard models are very almost the same from this viewpoint, because in this twisting argument, you don't have to care about the particle statistics. So one very interesting application was the Holden conjecture for this Heisenberg spin chain. So this is a standard model in quantum magnetism. But this quantum spin can be characterized by a spin quantum number, which can be 1/2 or 1 or 3/2 or 2 or whatever, a half integer or integer. But back in 1981, Holden boldly made a prediction or conjecture that this model is gapless only for half odd integer spins, like a 1/2, 3/2, 5/2, and it's actually gapped. So in some sense, a spin insulator for integer spins. And at that time, nobody expected this. So few people believed in this. So it was why this was called conjecture at that time. But eventually he was proved right. But again, so this, I guess, reflects this cultural difference. So if you are from condensed matter, gapless is kind of natural. But if you are from StatMech, actually the gapped phase is more natural, and you need some special reason to keep the system gapless. And indeed, Lipschitz matrix theorem is closely related to this phenomenon. And we can understand this in more general context. That is, you can always interpret spin system as a many particle system, although not electron system, but a bosonic system. Because for spin S, spin quantum number S, SD takes a value from minus S to S. So you can identify, let's say, SD equals minus S state as a vacuum. Then increasing SD by 1 can be interpreted as adding an extra particle, which is often called magnon. So SD can be written like a minus S plus particle number of magnons. Then magnetization per site is expectation value SD, which is minus S plus expectation value of number of particles. So this is nothing but the filling factor, which I had introduced. So magnetization per site is minus S plus nu. So in many antiferromagnet, at zero magnetic field, ground state has a zero magnetization. Then for zero magnetization state, this filling factor is nothing but S, spin quantum number. So this means that if you have half odd integer spins, like 1/2, 3/2, 5/2, then filling factor in this particle viewpoint is half integer, not integer. So Lipschutz-Matisse theorem applies. So you must have either ground state degeneracy or gapless spectrum. And that is why you have gapless ground state for half odd integer spins. But if spin quantum number is integer, then filling is integer. So at least Lipschutz-Matisse theorem allows trivial featureless spin insulator, just a unique ground state below the gap. And that is indeed the case for the ground state of standard high-grade chain. Of course, this does not prove that the ground state must be gapped and the trivial spin insulator, but at least Lipschutz-Matisse theorem allows, and this physical picture of integer filling allows such a trivial insulator with unique ground state, and that is most natural thing to do for the system in this viewpoint. And indeed, the system does in this. Okay. So yeah, so if you are familiar with Golden Gap business, then maybe you learn that the Golden Gap is related to the topological term of the nonlinear Singer model, which is present only for half odd integer spin S and so on, which is of course not incorrect, but kind of very abstract and hard to understand intuitively. But if you map this spin chain to many particle systems, then you can sort of intuitively understand the difference, because half of the integer spin corresponds to fraction filling, and the integer spin corresponds to integer filling. So it's natural to expect a trivial insulator. Okay. And that's one way to understand this Golden Gap problem. Okay, so I run out almost time, but I just wanted to mention some of the recent developments. So far, what I have discussed is what was known already in early 2000s. But yeah, recently this is also kind of very active topic to discuss. So one reason is that there are many generalizations found recently, and also new viewpoints. And as I discussed, in one dimension, we can apply original variation argument due to Lipschutz-Matisse. But if you go to 2-dimension and higher, then this variation argument doesn't quite work well. But still, you can derive a very similar argument, very similar result, essentially the same statement, also in higher dimensions. And that can be done by reinterpreting this Lipschutz-Matisse twist operator as a sort of gauge transformation, large gauge transformation. So yeah, so we know that electromagnetic fields can be understood as a U1 gauge field, then we can introduce a gauge transformation. But for the system with a primitive boundary condition, it has a non-trivial topology. Then it can be you can introduce a topologically non-trivial so-called large gauge transformation. And this large gauge transformation operator actually turns out to be identical to the Lipschutz-Matisse twist operator. And this viewpoint, okay, so I cannot explain why and how, but this viewpoint introduces many interesting generalization, especially because now this commutation relation between U twist operator and the translation operator I have introduced can be related to some sort of anomaly in field theory. And this viewpoint can lead to many generalizations. And I just, yeah, so including this kind of XYZ model without U1 symmetry. So from the original viewpoint, you cannot twist this system, or you cannot introduce a U1 gauge field because this has only discrete symmetry, but still the statement of the Lipschutz-Matisse theorem also applies to this system with only discrete symmetry. And also maybe more surprising example is this simple Hamiltonian without even usual Z2 symmetry, but this has some anomalous non-local Z2 symmetry. And yeah, they show that this has a gapless ground state for finite range of parameter. And yeah, it just confirmed their finding by exact generalization, and you can do this. So in this regime, the system is Tomonaga tangential, which is gapless. So this is protected by anomalous symmetry in some sense. So sorry for going over time to summarize. So yeah, metals are gapless and conducting, which might sound obvious to you, but this is rather non-trivial from StatMech point of view. Because the gaplessness or quantum criticality or conductivity is achieved either by fine-tuning of parameter or some sort of protection mechanism. And Lipschutz-Matisse type theorems provide at least some part of the protection mechanism of quantum criticality. And this has a long history of study, but recently this also became an active topic of current research. Thanks for your attention. Okay.
We have time for a few quick questions.
Obvious to me to what extent dimensionality plays a role here.
Yeah, good question. So the dimensionality is important because if you apply the original variation argument, then you can apply the same twist operator, then try to apply the same argument. Then the problem is that in variation argument, you evaluate the possible energy increase at each hopping. So every hopping term in X direction can increase energy by this twist. But now for this two-dimensional system, the number of bonds is proportional to Lx minus L1. And for each bond, the energy increases order of 1 over Lx squared. So if you multiply, total possible energy increase is order of Ly over Lx. So if you take isotropic limit, this is just order of 1. So you cannot say this is small. So if you take very, anisotropic summary limit by taking very long strip, then Ly over Lx can be made small. Okay, if you are satisfied this, then this still works. But there is a bit of subtlety about it. That's why we wanted a new argument for two dimensions.
Questions?
Just a quick question. So I understand how this Lipschutz-Matisse theorem in 1D distinguishes between spin half and spin 1, let's say. But how do you get that the spin half spin correlation is gapless? Because even in the Lipschitz matter scenario, you can have like a bunch of states which are gapless and then a gap, right? So then you won't get a.
Well, so yeah, for spin one half, for example, Lipschitz matrix theorem does allow a gapped state, but with at least 2 degenerate ground states. And indeed, that happens for XXD model, for example, if coefficient of SD is bigger than other couplings. So yeah, so this does not quite prove that the system is gapless, but in order to open up a gap, you must provide a ground state degeneracy, which is a bit harder than just opening a gap. So yeah, it just tells you you have to pay the price. But if you go to very incommensurate filling, like if nu is 999 over 1000, then you have to produce 1000 ground state degeneracy. Then so if the denominator gets larger and larger, it's more likely to have gapless spectrum. Yeah, for spin one half, Q is 2, so you just need to provide 2 degenerate ground states, which is possible. And depending on Hamiltonian, it actually does.
Okay, that is the last question. Okay.
So what is the, I mean, how this theorem is valid for if you have a mixed nearest neighbor interaction?
Yeah, there is no, as long as interaction or hoppings are short range, then there is no limitation. Yeah, because even if you twist, yeah, I just introduced nearest neighbor hopping for simplicity, but you can introduce next nearest neighbor hopping. You just have a e to 4 pi I over L. But as long as it's short range, you can apply the same argument. And also interaction doesn't care. So yeah, it's valid even if you include second neighbor interaction.
Okay, so let's thank the speaker.
So
Our next speaker.